So your resistance in this case essentially triples during this test, and that's a problem. But what's happening here is you're holding this device at a certain voltage. That changes the way that the chemistry is working, or the electrochemistry is working, and you're probably in this case getting some extra side reactions that are irreversible. Here's another example of cyclic testing, going up to 400,000 cycles. Just a different way of looking at it. This is a different source, but it's again a capacitor with an organic electrolyte. Your capacitance is dropping over nearly 400,000 cycles, only by about 15%, and your ESR is going up. So I think we probably said enough. I wanted to give you a flavor of examples that you'll see in the literature or you'll see in manufacturers' data on stability, so that you can understand, as you design a system, but also to understand that making the measurements that we talked about yesterday is important, because you have to go in at certain points in your cycle testing and make the capacitance measurement, make the ESR measurement. Now I want to do something a little bit different here to close out the second half of the lecture, which is to give you a foundation of a little bit more of a statistical foundation for how we quantify aging. Okay? So shown here is a Weeble distribution. You might have heard of that before, but I want you to look at the function. So F is the fraction that is unfailed, so not failed fraction, and it goes from 0 to 1. At the end, everything that you're testing has failed. And a function, this distribution that fits experimental data reasonably well, is shown here. You have a exponential factor where alpha is the characteristic life. So that's sort of the half-life here. Right, so that would be the age in the middle. Okay? And beta is the shape factor. So the beta determines whether that looks more like a soft, gentle slope up, or whether it looks like a very hard kind of a step function. Okay? So this distribution, we're going to be looking at these alphas and betas, especially the betas, as we go through the rest of the slide. So I want you to appreciate what that is. So here's an example of different betas. These curves are typical. This range of beta is typical of electrochemical devices. Beta values in the range of 5 to 15. That's an important number to look at. So you see that when the shape factor is 15, you end up with a steep steep upswing, and as the shape factor decreases, you get it loosens a bit. There also can be something called a bathtub curve. Okay? Just to add a little bit of a complication. And you probably know what this intuitively what this comes from. But the bathtub curve, this is the failure rate. That's how frequently you're seeing failures. It's not the cumulative distribution of failures like F is. This is the failure rate. And you see lots of failures at the beginning and lots of failures at the end. Okay, so this thing at the beginning, sometimes that's called infant mortality. It's a bit morbid, a term, but it's called infant mortality. So it's just, in many devices, because of manufacturing defects, assembly defects, that sort of thing, you'll actually have a lot of failures early in the device's life, and then you'll have a period of very low failure rate, and then at the end, as things really start to wear out, the effects that we're talking about today come into play, then you'll see an upswing in the failure rate. Okay? So in order to handle this, I'm showing you in the inset here, if you have very low shape factors, beta, right? If you have very low beta, then that can handle the early failures. it has sort of an effect of having early failure, capturing the early failures, and then you'd have to add. So this would be like a convolved two-function Weeble distribution, where you'd have one beta for the early failures and another beta for the late in life failures. So I think it's also important to understand what happens when you put lots of things together. So understanding the failure rate of one device or the failure statistics of one device is one thing. But you know then, if you have many of them in a system, then and you structure your system so that the failure of one brings about the failure of the entire system, then you have to appreciate that, you know, if you thought that your supercapacitor had a characteristic lifetime of, let's say, 1 year, but you have 50 of them in series, and if one of them breaks, then your system breaks, then of course that you can't say that you'd expect your system to last for 1 year. It would last for much shorter. So this is an effect of if you had 50 cells in series versus a single cell. So R is the reliability function. It's the inverse of the F function. And again, you'd see that your lifetime would decrease by about a factor of 2 with 50 of these cells. Okay, you could do the statistics on that. It's just you essentially are combining Weeble functions statistically. Well, how do you characterize a system? If you were in the lab and making devices, and I hope that you do this, I hope that you make redundant samples that you can test. You make a set of devices and test them under different conditions. In this case, we're looking at a voltage temperature experiment, right? And it's interesting to me because you actually have different test conditions, but inside of each condition you have redundancy. This is not often done in academic labs, where you take a test condition and you repeat it. Right? We say, well, if I'm going to take test conditions, I will just take ones, individual ones at each point. But the repeat testing is important because it can tell you, and it can tell a statistician, how confident you are that the data at that point are valid. Right? Because if you make a mistake in one point, if something goes wrong unusually, like this infant mortality thing, then it will ruin the rest of your experiments. It will lead you to false conclusions. And so having redundancy in your experimental design is important. But I would say that we don't teach, even in engineering, we don't teach design of experiments that well, at least where I am. Maybe other places do. But certainly, this, in the manufacturing world, this is much more accepted and common. And so we haven't taught it rigorously, I think, in engineering for the most part, and I'd like to do better. But one of the problems is that historically you kind of always had to be a statistical expert in order to design the experiment, and you had to hire a statistician or something like that. But what's happened recently is that there's a number of good software developments where you can you can apply these principles pretty easily. And I think with a relatively low risk of abusing the statistics. So what we do in my lab is we use a software called Design Expert. This is an example of how you would set up an experiment in Design Expert. You would take your factors. I've just listed them here, A, B, C through E. And I've assigned them on a relative basis how difficult or easy it is for me as the experimentalist to change that factor in my experiments. That's also something that's, I think, relatively new. So you can actually design your statistics around how difficult it is for you to execute your experiments, and then you give the number of levels that you have of each factor, 1 and 2. In this case, it's a very, very simple design. This would be a type of design that you would use for screening. You would be screening main effects. You'd be asking the question, does factor D have a big effect on my result? You wouldn't want to be building models around the effect of D from a design like this. You would just have a high and a low value for D and see if it has a big effect. And then maybe later you would go through a more rigorous and thorough assessment of your parameter space, but you would do so only using the variables that you found in your screening experiment had a large effect. Okay? So here's an example. This is actually an example where we're making the material, not doing a supercapacitor test yet. And I'm just showing a couple of factors. We have 5 total factors in this experiment. It's a plasma CVD experiment where we have 3 different gases, argon, methane, and hydrogen. And then we can also adjust the pressure in the reactor and the power. That's the plasma power that we use. And using something called a D-optimal design, which is used for kind of in-between screening and kind of full model development. That's where D-optimal sits in the statistical world. The program itself will make up a set of experiments. Okay? And in fact, you could see that the color coding here, you could actually see the font is a little bit small. There are redundancies in the sample set here. I'm only showing 2 dimensions. I'm showing methane versus pressure, but of course there are 3 other dimensions in the experiments. I just can't show them easily on a 2-dimensional screen. But there are a number of points that are redundant. In fact, the way that the software designs it is the corner points are often the ones that are made to be redundant, because those are the edge of your boundaries. And then you'll also notice that it tends to put things at the boundaries and then in the middle. There's that band in the middle that is emphasized in this designed experiment. Okay, because that's going to give you your edges where you tell the program I can't go higher or lower than these 2 things, and then in the middle that allows for a better statistical distribution of your process. You could also vary other factors, and you could put constraints on your system. So in our case, we don't want to have a power, the microwave power, to be too high for a given pressure, but that maximum power changes as pressure increases. So as pressure increases, we can accommodate more plasma power. There's better cooling from the gas in the system. So you end up seeing these diagonal boundaries in your design space. So you could actually design constraints into your system so that you're not breaking things as you go. That's also important for the experimentalist. And you see again, look at the methane versus argon figure on the right. You'll see that there's a bunch of points clustered right around the middle of that space. That's what the statistics do for you. If you were just picking on your own, I imagine you would be like I am. I would start to populate the space all through this parallelogram, right? Evenly. That's probably what I would do, but the statistics say you shouldn't do it like that. You should be focusing on the edges and the middle. Here's an example going back to electrochemical cells. Here's an example where I don't have nearly as much ability to conclude experiments as I do in a material growth, right? It's very hard to make an entire battery or supercapacitor. So I only have 6 samples. But this is what the cumulative failure function would look like. This is on a log chart, right? But I have 6 samples, and I failed all of them in my test. And they failed in a range that was reasonably close, right? Between 1,017 and 12,071 hours. And so from these 6 samples, we can actually analyze the Weeble function. In this case, the shape factor beta is 15.7. I told you before that it's typically between 5 and 15, so that's consistent. Of course, those aren't hard limits at all. The mean time to failure is 1183, right? And so you can actually get a fairly strong set of conclusive results with just 6 samples in this case. Okay, but I'm only really looking at one output factor, which is the failure. Another thing, so looking at correlation between factors is important. It's another thing that the statistics can help you do. This is a correlation between voltage and temperature. So if we look at this, we're looking at 3 different voltages, and we ran experiments to look at failure. This is not, I didn't do this, this is an example from the literature, but they ran 3 different voltages as a function of temperature. If the voltage effect did not interact with the temperature effect, then what you would expect to see is that these 3 curves are parallel, right? In this case, what we find is that 2 of the curves are parallel and 1 is not parallel with the other 2. It suggests that there is a correlation between voltage and temperature in your experimental results. Okay. So just to close us out here,